Hello viewers, we're gonna review a paper with me, Elsie, and my friend Joana. And today we're gonna talk about new and colony optimization algorithm for the traveling salesman problem. So here for the outline, we have author information, introduction, traditional ACO, new ACO algorithm, simulation experiment, discussion, conclusion, and last but not least, we have advantage and disadvantage. So we're gonna start with the author information here, and the title of the paper is New and Colony Algorithm for the Traveling Salesman Problem, as what I say at the first. So this paper is written by Wei Gao, and he is from College of Civil and Transportation Engineering, Hohai University, Nanjing, Jiangsu, China. And this paper was published in International Journal of Computational Intelligence System. Okay, before any further ado, let me tell you about this paper. So, what is ACO or Ant Colony Optimization? Okay, basically ACO is an algorithm used to solve combinatorial optimization problem. ACO has been applied to various optimization problems, including the traveling salesman problem or TSP, and the other problems. But in this paper, we're gonna using TSP for the use case. Okay, we all know that ACO has shown good result in terms of solution quality and stability, right? But it has limitation in terms of complexity and scalability too. Why? It's because traditional ACO can only be used for small scale problem. So we need more scale, right? Okay, so because of that, this research will introduce you a new ACO algorithm that aims to address the limitation of traditional ACO methods. And this algorithm incorporates a mapping strategy to enhance diversification and maintain a balance between intercertification and diversification. It also introduces you a new transition rule and a dynamic updating rule for heuristic parameters using entropy to improve performance. Okay, let's jump to traditional ACO. Overall, this chapter will describe you how a traditional ACO works in solving TSP, including the initialization step, calculation of the probability, pheromone update, and the iterative stage in the ACO process. But to make it easier, we have summarized it in a few points for you. So for the first point, we have initialization. Okay, at first, ants are randomly placed in different cities. So all paths have the same pheromone intensity, which is usually represented by constancy. For the second point, we have selecting city. Means each ant select the next city that it has not visited based on probability calculated using pheromone information on the paths and heuristic information about the path length between cities. For the third point, we have tabulus. What is tabulus? Tabulus is to avoid visiting the same city more than once. Each ant has a tabulus that records the city it has already visited. For the next point, we have pheromone update. Once all ants have completed a cycle or visit all cities, the pheromone intensity on the paths must be updated. The pheromone update involves subtracting some of the existing pheromone and adding new pheromone based on the length of the tour discovered by each ant. And to choose how pheromones are updated based on various information, there are three general descriptions. For the first one is global information, first local information, and the second local information. So for the first one that we call the global information, this is an approach that uses global information about tour discovery by key ant. This is mean that ants that discover shorter tour will make a greater contribution to pheromone enhancement to those pets. And for the second one, this is the local information one, or the first local information. This is an approach that focuses more on local information, i.e. the length of the path between city I and G. This is mean ants will be more likely to increase pheromone on shorter paths. So for the third one, this is what we call second local information. This is an approach that focuses heavily on local information, regardless of the path length between city I and G. It can be used when customization based on path length is not desirable. So if in the previous discussion, initially in traditional ACO, ants will choose city with high flexibility. However, at the end of the search, ants select city without diversification, which reduce the ability to explore other potential paths. It is argued that this may result in fast convergence but weak diversification. So, in this new rendezvous strategy was introduced to increase search diversification and maintain the necessary intensification. It is explained that encounter between ants occur when about half the city has been visited. The ant pair that meet combine their tablets to create a new tour, and pheromones are added to this new path. And to control the search process, a constant threshold fee is used. If the number of ants encountered exceeds this threshold, the search stops and the pheromone is stored on the new tour. Otherwise, the search continues until all tours are formed. Okay, the pheromones update according to the following equation. So for the first one is this equation is used to calculate how the pheromone on a path will be updated based on information from all ants in the population. This update is important because what? Because this is the pheromone direct other ants to choose a path that has proven effective in finding a solution. The second one is the equation is used to ensure that the pheromone value on each path stays within the specific interval, which is in turn help achieve a balance between exploration or diversification and intensification or information gathering. So, in this the new ACO algorithm, a new tour created by meeting ant is visited by two ant instead of one is in traditional ACO. There is a limitation strategy for the value of the pheromone use. The use of a confluence strategy ensures that ants at the end of the search can still choose from the variety of cities, thus maintaining their exploration capability. So in this new ACO algorithm, the search time will be greatly reduced and the disverification of the search in the ant colony will develop rapidly. So here is the flow chart of a new ant colony optimization algorithm. In this new algorithm, the termination condition is that the length difference for the optimal paths of neighboring iteration is less than 10 till 5. In addition, to avoid infinite iteration, the maximum number of iteration and is given. Alright, for the next chapter, will be continue and explain it by my friend, Joanna.
Now we proceed to delve into the simulation experiment section to address topics related to problem solving. The study evaluated a new ACO algorithm using various TSP instances from the TSP-LIB benchmark library. Parameters of the new algorithm can be determined to be alpha equals 1, beta equals 2, and the others. The algorithm used an equal number of ANDs and cities with the threshold constant set to 1 for optimal performance. Averaging results from 30 runs, experiments were conducted on laptop with Intel Core i5 3.4 GHz CPU and 32 GB of RAM. Percentage deviation formulas used in this study are as follows. PD best percent equals best solution minus optimal solution slash optimal solution multiplied by 100. PD average percent equals average solution minus optimal solution slash optimal solution multiplied by 100. Table 1 summarizes the new ACO algorithm's performance across 20 TSP instances, showcasing its capacity to approximate optimal solution closely. Deviation below 0.5% in 7 instances, an efficient operation with most cases completed in under 30 seconds and 500 iterations. In Table 2, among 16 algorithms considered, the BAA and HMMAS algorithms performed poorly, while the SA, SOSOA, DBA, DCSA, and the proposed algorithm showed strong performance. In Figure 2 and Table 3, when comparing four promising algorithms across 15 TSPs, in the new algorithm demonstrated excellence in PD-best, with SASOSOA as the top performer, while it lagged behind in PD average. It remained competitive with DCSA and DBA, surpassing the latter. Overall, the new ACO algorithm showcased effectiveness in approximating optimal solution, computational efficiency, and competitiveness among state-of-the-art counterparts, except for a few standout algorithms like DBA and SASOSOA. Let's move on to the discussion section to explore and analyze the topics in more detail. A comparison between the new ACO algorithm and traditional ACO is conducted to assess performance. The traditional ACO parameters are as follows, and the new ACO algorithm parameters are as follows. It's important to note that these parameters are kept the same for a fair comparison, even though they may not be the most suitable values for both algorithms. In this study, we evaluated 8 TSPs as follows. The analysis was based on the RE metric defined as RE% equals solution from traditional algorithm minus solution from new algorithm slash solution from traditional algorithm multiplied by 100. 4 consistently shows the new ACO algorithm outperforming traditional ACO in all HTSP with RE values mostly below 1%, even in worst-case scenarios where RE stays below 10% on average. Table 5 comparison of statistical results for the new ACO algorithm and traditional ACO for 8 TSPs. Figure 3 compares the result using statistical measures, including coefficient of variation and relative error. The new ACO algorithm consistently outperformed traditional ACO, with smaller computational relative error averaging 0.0075%, 0.82%, and 0.98%, and more uniform solution, indicated by an average coefficient of variation of 0.98 compared to traditional ACO's 1.62. Moreover, Figure 4 reveals that the new ACO algorithm consistently achieves faster computing speeds than traditional ACO across all TSPs, with this speed advantage becoming more pronounced as problem complexity increases. Levels quantifies the reduction in computing time by the new ACO algorithm, with reduction rates ranging from 41.1% to 52.4%. This signifies significant time saving as problem complexity increases, notably when comparing the rate of time increasing to problem scale. The new ACO algorithm consistently outperforms traditional ACO. In summary, the new ACO algorithm consistently excels in solution quality, stability, and computational efficiency when compared to traditional ACO. This makes it particularly well suited for complex combinatorial optimization problems, attributed to its more frequent utilization of a mapping strategy as problem complexity grows, resulting in faster and more reliable results. Now we arrive at the conclusion section to summarize and draw final insight from our findings. In summary, the innovative ACO algorithm effectively addresses common ACO challenges and outperforms established competitors in solving TSP problems. 1 in 20 out of the chosen TSP instances, the new ACO algorithm consistently found optimal solutions, with only 7 exceptions. Moreover, in the 30 trials conducted, the average solution closely approximated the optimal solution for most cases. 2. SA, SOSOA, DBA, DCSA, and our algorithm consistently achieve optimal solution, with average solution often matching the optimal one. 3. The new ACO algorithm is notably more stable and aggregated compared to the traditional ACO, indicating its potential to substantially change the traditional algorithm. 4. In-change computing precision and speed were observed in our algorithm compared to traditional ACO. 5. Notably, our new ACO algorithm's computational efficiency increased with problem complexity, showcasing superior performance as intricacy grew. Lastly, let's examine the advantages and disadvantages of this journal to gain a comprehensive perspective on its merit and limitation. A notable of this journal article lies in its introduction of a fresh ACO algorithm tailored for solving the TSP. Through comprehensive comparisons with traditional ACO and contemporary algorithms, the study showcasing promising outcomes in terms of both solution quality and computational speed for TSPs. Disadvantage: a limitation of the journal article is its constrained testing scope, as the newly proposed ACO algorithm primarily undergoes assessment on relatively small-scale TSPs. The article acknowledges that with larger TSPs, there can be a rapid increase in computational complexity, potentially impacting computational efficiency. In closing, we have truly explored the various aspects of our subject matter. Thank you for your attention and engagement throughout this discussion.